There's a channel of water up on top of a bridge in the south of France. It's a stone trough, barely wider than your shoulders, running along the very top of 3 tiers of arches about 160 feet up in the air. And the water in it is moving. It's not sitting there. It's flowing steadily in one direction, the way water in a river flows downhill. Except this is not a river. There is no spring on top of that bridge. The water started its journey in some hills tens of miles away, and it is on its way to a city it has not reached yet. So walk along that channel with me for a second as an engineer and start looking for the thing that has to be there. Look for the pump. Look for the pump house, the machine, the wheel, the engine, the thing that is pushing all this water across the countryside and over this valley. Because water does not move itself. Something has to lift it and push it and keep it going for mile after mile after mile. You will not find it. There is no pump. There is no engine. There is no machine of any kind, anywhere in the entire system, from the spring to the city. Not one. And the whole thing was built 2,000 years ago. So how exactly is this water getting where it's going? My name is Dan, and I've spent about 25 years as a structural engineer. I've stood in the mud on more building sites than I can count, in a hard hat, holding a set of drawings that already went out of date this morning, arguing with somebody about a budget. And I have to tell you, there is a very specific feeling I get when I look at what the Romans did with water. It is not just admiration. It's closer to envy, because I know in detail exactly how hard the thing they did is. I know what it takes to move water across a landscape, and I know what it costs, and I know all the ways it goes wrong. And they did it with no pumps, no motors, no computers, no cranes, and no electricity. And some of what they built is still standing, and a little of it is still running water, right now, today. So let me walk you through how they actually pulled it off, because every single step of it is more clever than it has any right to be. Let's start by throwing out the picture in your head. When people hear the word aqueduct, they think of that bridge, the big row of arches marching across a valley. That's the postcard. But that bridge is maybe a tiny fraction of the whole thing, the dramatic bit, the part that had to cross a gap. Most of a Roman aqueduct you would never see at all, because most of it ran underground in a covered channel, buried in a trench or tunneled through the rock. They put it underground on purpose. Underground, the water stays cool and clean. It doesn't evaporate in the summer sun. It doesn't freeze as easily in winter, and nobody can walk up and foul it or tap into it or wreck it. The arches only come out of the ground when the engineer has run out of options, when there's a valley in the way that he simply has to get across. And here is the one idea you need to hold onto for the whole rest of this, the thing that makes it all work. There is no pump because there does not need to be a pump. The entire system runs on gravity and only gravity. The spring is up high in the hills. The city is down low. And in between, the whole way, the water is always going very slightly downhill. It never climbs. It never goes up. The channel is tilted ever so gently downward the entire distance, so the water is quite literally just falling in extreme slow motion all the way from the mountains to your fountain. That's it. That's the secret. And I know that sounds simple, almost like a letdown. But hold on, because simple is exactly what makes it insanely hard. Here's the problem hiding inside that simple idea. If the water is only ever going downhill, then your spring has to be higher than your city. Fine. But it can only be a little higher, because if your channel drops too steeply, the water rips down it like a flume. It slams into the far end. It sloshes and overtops and tears the lining out of the channel and destroys itself. Too steep is a disaster. But too flat is worse because if there's not enough slope, the water just stops. It sits there, it goes stagnant, it silts up, and your aqueduct is a very long, very expensive puddle. So you have to thread the needle. You need a slope that is steep enough to keep the water moving, but gentle enough that it moves calmly. And you need to hold that slope, without a single mistake, for the entire length of the thing. And when I say gentle, I need you to really feel this number, because this is the part that stops me cold every time. Take that aqueduct in France, the one that feeds the city of Nimes, the one that crosses the famous bridge. Over its whole length, the ground it covers, the water drops on average something like a foot for every mile or two it travels. There are stretches where the fall is just a few centimeters over an entire kilometer. A few centimeters over a kilometer. Now, the exact figures get argued about because the modern measurements don't perfectly agree, and some of the ancient sections are gone. So I don't want to nail it down to the last millimeter and pretend it's gospel. But the order of magnitude is not in doubt, and the order of magnitude is absurd. We are talking about a slope so slight that if you stood in that channel and looked down its length, you would swear on your life it was dead flat. Your eye cannot see that slope. Your eye is not good enough. So let me put that in terms of my own working life, because this is where the envy really kicks in. On my sites, to get a slope like that right, I use a laser level. I've got a little box on a tripod that spins a laser beam in a perfect flat plane, and a sensor that beeps when it's dead on, and it will hold a grade to a couple of millimeters over a room. And even with that, even with a laser, my crew gets a fall wrong on a drain run, and I have to make them dig it up and do it again. The Romans held that grade, that same ridiculous, invisible few centimeters per kilometer grade, across tens of miles of open country, over hills and around valleys. And they did it by eye and by hand with no laser and no lens, and as far as we can tell, no math beyond arithmetic. So how? How do you find level and hold a grade that fine without any of my toys? This is where I want to introduce you to two beautiful pieces of equipment, and I know the names sound like spells, but stay with me. The first is called the chorobates. Picture a long, heavy wooden bench, straight as they could make it, maybe 15, 20 feet long, standing on legs. Along the top edge they cut a groove, a little channel, and they poured water into it. Water, sitting in a trough, will always find its own perfect level. That's just physics. And if the bench is tilted even slightly, the water pools to the low end and you can see it. They also hung plumb lines, weights on strings, down the sides against marked scales, so gravity itself drew them a vertical reference. Between the water and the weights, that heavy wooden bench could tell them right here at this spot which way is truly level and by how much I'm off. It is a spirit level the size of a park bench, and it works on nothing but water and gravity, the same two things the aqueduct itself runs on. I find that genuinely poetic. The second instrument is called the dioptra. This one is a sighting tool, a disc or a frame mounted so it can swivel and tilt, with sights on it like the sights on a rifle, so a surveyor could look through it, line up on a distant marker held by another man far away, and measure angles, both across the land and up and down. It is, in every way that matters, the great-great-grandfather of the instrument my survey crew still sets up on a tripod today, the theodolite. Same idea. Sight a target, read an angle, move your target, repeat, and inch your line across the countryside one careful shot at a time. And we're not guessing that they had these things, by the way. This is where I get to hand you the one solid fact I want you to walk away with. We have the Romans' own writing about it. A man named Vitruvius wrote a whole set of books on architecture and engineering, and he describes the chorobates and how to survey a water channel. And even better, a man named Frontinus, who was literally put in charge of the water supply of the city of Rome. The water commissioner, around the year 97, wrote an entire report on the aqueducts, how long they were, how much water they carried, how they were maintained, where people were stealing from them. It is a real document by a real official doing a real job I completely recognize, and it survives. When I say we know how they did this, that's what I mean. They told us. Now let me be honest with you about what that precision actually costs, because I live this part. Holding a grade that fine is not really an equipment problem. It's a discipline problem. It's 100 men over months, and every one of them has to not cut the corner. And I know, from painful experience, exactly how that goes. I've got a foreman, good guy, sharp guy named Mike, and Mike's whole religion is getting the job done and moving on. And Mike, God love him, if he thinks a fall is close enough, he will call it close enough, backfill the trench and be 3 sections down the line before I've checked it. And close enough, on a slope this fine, is another word for broken. The Roman surveyor did not have that luxury. If his gang got lazy on one section, if they let the grade drift flat for a couple 100 yards, the water would pool there forever, and there was no fixing it without tearing the whole run open. So the astonishing thing about that gentle slope isn't really the surveying. It's that they made a small army of human beings hold a standard that I struggle to get 3 guys to hold on a Tuesday. That's the part I can't get over. Okay. So you've surveyed your gentle downhill line across the country, mostly underground, sweet and cool and hidden. And then you hit a valley. The ground drops away in front of you, a big gap, and on the far side it comes back up to roughly the height you need. Your water is up here, at your precious grade, and if you follow the ground down into the valley and back up the other side, the water goes down, fine, but then it cannot climb back up, remember, it only ever goes downhill. So you can't just drape the channel over the terrain. You have to carry your water across that gap in the air, keeping it at almost exactly the height, keeping that same invisible grade going, right across the empty valley. And that is what the arches are for. That postcard bridge, the Pont du Gard, the one we started on, that's the answer to a valley. 3 levels of stone arches stacked on top of each other, the big ones on the bottom, smaller ones up top, marching across the river gorge to hold that little water channel up in the sky at exactly the right height. It stands around 160 feet tall, and here is the detail that makes me want to lie down. The biggest stones in it weigh several tons each. They were cut, hauled, lifted, and set without a hydraulic crane, without a diesel engine, using timber cranes powered by men walking inside a giant wooden wheel like a hamster, levers, ropes, ramps, and an appalling amount of human muscle. And they cut those stones so well that the arches were laid dry, no mortar in the big structural stuff, just stone resting on stone, shaped so precisely that the weight itself locks it all together. That's the arch. That's the whole magic of Roman building, honestly, and it's worth 30 seconds. An arch is a way of crossing a gap using stone, and stone is a material that is fantastic at being squeezed and useless at being stretched. Pull on stone and it cracks, but shape a row of wedge-shaped blocks into a curve, and every block is trying to fall down, and in trying to fall down it jams against its neighbors, and the whole thing squeezes itself tighter the more load you put on it. The load doesn't pull the stone apart, it pushes it together. An arch is a bridge that gets stronger when you lean on it. The Romans didn't invent the arch, but they understood it cold, and they built their entire world out of it. And 2,000 years later, I am standing underneath one that is still holding up its own weight with zero maintenance. No inspections, nobody in charge of it, and it has not so much as sagged. My structures come with a design life and a maintenance schedule and a big list of assumptions about somebody looking after them. This thing was just abandoned, and it refused to fall down. But arches have a limit. An arch bridge is expensive, and it gets absurd fast if the valley is really deep, because to keep your grade you'd need a bridge hundreds of feet tall, and stacking stone that high just to hold a water trough is madness even by Roman standards. So what did they do when the valley was too deep to bridge? This is my favorite part of the entire subject, and it's the part that genuinely bends my brain, so let me build it up carefully. They used something we call an inverted siphon. Here's the idea. Instead of carrying the water across the top of the valley on a bridge, they took the water and they sent it down. They put it into a sealed pipe, a proper pressure pipe, usually made of lead, sometimes of stone drilled through, and they ran that pipe down the near slope of the valley, along the bottom, sometimes across a modest low bridge at the very bottom, and then back up the far slope. The water dives down one side of the valley and climbs up the other. Now stop, because your gut is screaming the same thing mine did. The water goes uphill, on the far side. Didn't you just spend 10 minutes telling me water only ever goes downhill? And the answer is the beautiful bit. Water in a sealed pipe will rise back up on its own with no pump, as long as it doesn't have to rise quite as high as where it started. You felt this. It's the same reason water finds its own level in a U-shaped tube. Fill a U with water and both sides settle to the same height, no matter the shape of the bend at the bottom. The weight of all that water pouring down the entrance side has real pressure behind it, and that pressure shoves the water back up the exit side, and it will climb almost all the way back to the level it fell from. So the Romans would drop their channel into a header tank on the high side, let the water pour down into the sealed pipes and across the valley floor under enormous pressure, and let it come surging back up into a receiving tank on the far side, just a hair lower than where it left, and then it quietly went back to being a gentle open channel again, and carried on toward the city like nothing had happened. No pump. Just pressure and patience and a really, really good understanding of how water behaves. You can go and see where they did this. At Lyon in France, the Roman city there was fed by aqueducts that used these pressurized siphons with pipes of lead to cross deep valleys. Thousands and thousands of pounds of lead formed into pipe. There's a spectacular one at a place called Aspendos in Turkey. These were the crown jewels of the whole system, the hardest, most dangerous thing they built, because that pipe at the bottom of the valley is holding back the full pressure of a towering column of water, and if a joint blows, it blows hard. Lead pipe, hand-formed, hand-sealed, holding serious pressure at the bottom of a valley with a small army working around it. Try getting that past a modern safety inspector. I actually got asked the perfect question about this once, by an intern on my site, a young engineer named Priya, who is one of those people who asks the thing everyone else is too proud to ask. She looked at a drawing of one of these siphons and she said, if they could build a pressure pipe that pushes water back uphill, why did they ever bother with the arches at all? Why not just use the pipe for everything and skip the giant bridges? And I stood there for a second, because it's a genuinely brilliant question, and the answer tells you everything about how good these people were. Pressure is dangerous and expensive. That lead pipe under pressure was costly. It took a fortune in metal, it leaked, it burst, and it was a nightmare to maintain. The open channel up on the arches is cheap to run, easy to inspect, easy to clean, and it just sits there working for centuries. So they used the calm, boring gravity channel wherever they possibly could, which was almost everywhere, and they only reached for the scary, expensive, high-pressure siphon when a valley left them no other choice. They weren't showing off. They were doing a cost-benefit analysis. They were value engineering a water system in the 1st century, making exactly the trade-off I make on every job, cheap and reliable versus expensive and clever, and they were making the right call. I have sat in meetings having that identical argument 2,000 years later with a laptop. Now let's talk about what all of this was actually made of, because there's a material secret here that we are, honestly, still catching up to. To line these channels and seal these tanks and build in wet places, the Romans had concrete. And Roman concrete is one of those things that sounds boring and is actually one of the great inventions in human history. Ordinary lime mortar, the standard glue of the ancient world, has a problem. It sets by reacting with the air, and it does not like water. Put it underwater and it doesn't harden properly, it just turns to mush, which is a real problem when your entire business is water. But the Romans found something. Down near Naples, near a town called Pozzuoli, there's a particular volcanic ash, and when you mix that ash with lime and water, something different happens chemically. It sets hard even underwater. It doesn't need the air. You can pour it into the sea and it will cure into solid rock beneath the waves. They called the ash after the town. We still call that whole family of materials pozzolana after Pozzuoli to this day. Think about what that unlocks. Suddenly, you can line a water channel with a material that is happy being permanently wet. You can waterproof the inside of your aqueduct with a special render, crushed pottery mixed into lime, packed into the corners, that shrugs off water for centuries. You can build harbor walls and piers straight into the sea. There are Roman harbor structures that were poured into open water 2,000 years ago and are still solid. My concrete, the stuff we pour today, is stronger than theirs on day one. I'll give us that. We can hit crushing strengths they never dreamed of. But here's the thing that keeps me up. Modern concrete has steel inside it, reinforcing bar, and over decades water gets in. The steel rusts, the rust swells, and it cracks the concrete apart from the inside. We design our concrete structures with a life of, honestly, often 50 to 100 years, and then somebody has to deal with them. Theirs has no steel to rust, and it has been sitting in seawater since before England had a written language. And it gets stranger, and this is genuinely recent, so let me flag it clearly. In just the last few years, researchers have been arguing that Roman concrete may actually be able to heal its own cracks. The idea is that little lumps of unreacted lime left in the mix act like tiny first aid kits. When a crack forms and water trickles in, it reacts with those lime lumps and deposits fresh mineral right into the crack, sealing it back up. Now, I want to be straight with you. This is new science, and it's being debated, and not everyone agrees on how much the Romans did this on purpose versus how much it's a happy accident of how they mix things hot. So take the self-healing story as a promising, exciting idea that people are still fighting about, not as settled fact. But even the fight over it tells you something. In the year 2026, we are running experiments to try to reverse engineer the recipe of a concrete that a Roman foreman knew by heart. I don't want to leave you with the fairy tale that they built it and walked away and it was perfect, because that's not engineering and it's not true. These systems were a maintenance headache, and I love them more for it because it makes them real to me. The water in a lot of these regions is hard, full of dissolved lime, and as it flows for years it lays down a crust inside the channel, a stony scale we call sinter, thicker and thicker, until it starts to choke the flow. There are aqueduct channels where you can still see that crust, inches thick, built up on the walls. So they had gangs of workers whose whole job was crawling through these channels, in the dark, chipping that scale off the walls to keep the water moving. Frontinus, our water commissioner, spends a good chunk of his report basically complaining about maintenance and about people illegally tapping into the pipes to steal water for their gardens. 2,000 years later, I promise you, water utilities are having the exact same two problems: scale in the pipes and people stealing the supply. Nothing is new. And here's a place where they got something wrong, to their credit, that we can even tell. A lot of the pipework, especially those pressure siphons, was made of lead. And lead, we now know, is poison. The remarkable thing is that Vitruvius, their own writer, actually warned that lead was unhealthy and that clay pipe made for better tasting water. He flagged the risk. They mostly carried on using lead anyway, because it was workable and it held pressure, which, again, is the most human engineering decision imaginable. We know this material has a problem, but it does the job and the schedule's tight. So, in practice, the scale we just talked about, that lime crust, often coated the inside of the pipes and put a barrier between the water and the lead, which probably softened the worst of it. But I'm not going to sit here and pretend they got everything right. They didn't. They were engineers making calls with incomplete information under pressure, which is to say, they were us. And that's actually why I can't be too smug about my own record either. I ran a job a few years back that came in at, and I am not exaggerating, 200% over its original budget. Double and then some. Permits, ground conditions we didn't expect, a design change halfway, the usual death by 1,000 cuts. Modern project, modern tools, modern everything, and we still blew the number to pieces. So when I look at a system like the aqueducts of Rome, 11 of them eventually, running for hundreds of miles, maintained and extended over centuries, I don't just see clever engineering. I see project management that makes mine look like a joke. And here's the turn, the thing I saved for you, the fact that honestly gives me a little chill every time. This isn't all ruins and history and stuff behind a rope. In the city of Rome, right now, there is water coming out of fountains that is being delivered, at least in part, along the line of an aqueduct the Romans built. One of their aqueducts, one they finished before the birth of Christ, has been repaired and rebuilt over the centuries, sure, but it still runs, and it still feeds fountains in the middle of the city. When tourists throw a coin into that huge famous fountain in Rome and make a wish, the water they're looking at got there down the line of a 2,000-year-old idea. The thing is still doing its job. Sit with that against how we build. I have watched a stadium get demolished that was younger than me. I've seen car parks and bridges and whole buildings, things built with computers and steel and cranes and every advantage those Romans never had, get torn down and replaced inside a single human lifetime because they were at the end of their design life, which is a polite way of saying we plan for them to wear out. We build things to last 50 years. On purpose. It's in the spec. And these people, with water and gravity and stone and a wooden bench with a puddle in it, built things that are still delivering drinking water after 20 centuries. So here's what I actually take away from this, standing on my muddy site in my hard hat, a little bit jealous of some engineers who have been dead for 2,000 years. It's not that they were smarter than us. They weren't. I don't have a mystical thing about the ancients, And if anyone ever tells you these were built by aliens or some lost super civilization, please close the tab. It's an insult to the very real, very human, very tired surveyors who actually did this with their hands. It wasn't magic. It was a bench, a siding tube, a good understanding of water, cheap where possible and clever where necessary, and an unbelievable amount of patient, disciplined human labor. Every trick I showed you, you could explain to a sharp 15-year-old in an afternoon. The difference isn't intelligence. The difference is what they were building for. They built like the thing was supposed to outlive them, outlive their children, outlive their empire, become part of the landscape. And somewhere along the way, we stopped doing that. We build for a budget cycle and a design life and a warranty period. We build things we already know we're going to knock down, and I catch myself doing it on my own jobs, signing off on a 50-year number without blinking. And I wonder what it would even feel like to build something the way they did, like it was meant to still be standing when everyone who remembers me is gone. So that's my real question for you, and I mean it. I'm not just saying it. Look around at whatever it is you make. Maybe you build actual things. Maybe you write code. Maybe you're raising kids. Maybe it's a business, a garden, a body of work. Are you building it for 50 years, for the warranty period, for the quarter? Or are you building it the way the Romans built that channel in the sky, like it's supposed to still be carrying water long after you're gone? Tell me down in the comments. Genuinely, I read them. What's the thing in your life you're actually trying to build to last? And what's the thing you know full well you're building to the minimum and quietly planning to tear down later? I want to hear it, engineer to engineer, and I promise you're not the only one with an answer to that second one. I'm Dan. If you like standing under 2,000-year-old structures and quietly panicking about how good they are, that is the entire point of this channel. So stick around and subscribe, and I'll take you inside another one of these things that absolutely should not still be standing, and is. Next time somebody tells you the ancients were primitive, you tell them about the water going uphill in a sealed pipe, with no pump, at the bottom of a valley in France 2,000 years ago, and then ask them to build one. I'll see you on the next one.